answer? Okay. So the yesterday slides you received already. One of the thing is for tutorial questions, yeah? Yes. Yeah. So in that tutorial, we have some question on how to design space-time block code, etc. And the performance analysis, etc. We will do some question in the afternoon. You will understand more about by doing so, how do we get diversity 2 or more, etc. Okay. So now I'm going to move to kind of a MIMO case. So MIMO, spatial multiplexing, capacity, multiplexing architecture, and precoding. So this is the very important stuff. Hopefully I will talk tomorrow as well. This is the foundation lead to 4G and 5G as well. Okay. So until 3G, we were using CMO or MISO kind of a channel. We didn't use the full MIMO channel, multiple and transmit and multiple receive. And 4G onwards, it become MIMO and messy MIMO architectures are deployed. Okay, so the next slide set of slides is going to talk about MIMO, spatial multiplexing, capacity, multiplexing architecture, and precoder. So the main story, we start with the okay, I already talked about that. We start with single input, multiple output, and multiple input, single output channel. They provide diversity, and they also provide power gain, but they don't provide a degree of freedom gain. So I will tell you what is the degree of freedom gain later on. So the MISO and CMO channel, if you do a receiver beamforming or transmitter beamforming, it will give you a power gain and also give you a diversity gain, but it won't give you another gain called degree of freedom gain, okay, or spatial multiplexing gain. I will tell you about what does that mean. The MIMO channel is going to give you a degree of freedom gain and the spatial multiplexing gain. Okay, degree of freedom gain is most usual in high SNR regime. As I said, we always talk about high SNR and low SNR. So those things, so in the degree of freedom is very prominent in the high SNR regime. Okay, MIMO channel have a potential to provide a degree of freedom gain, and so I will show you about that. And then I'll talk about capacity of the MIMO fading channel, nature of the gain, okay. We have both degree of freedom gain and the power gain. Then I will talk about transceiver architecture for fast fading channel for the MIMO case. That's called VBLAS, Vertical Bell Laboratory Layered Space-Time Architecture. Then I'll talk about transceiver architecture for the slow fading channel. That's called DBLAS, Diagonal Bell Laboratory Layer Space-Time Architecture. Hopefully, tomorrow morning I'll talk about multi-some MIMO, downlink precoding techniques. Then that will lead to messy MIMO stuff as well. So that's the plan for today, rest of the today and tomorrow. So we already seen this one, transmit, this is the CMO channel or receiver beamform, receiver diversity. This is a MISO channel, transmit diversity. This is both transmit and receiver diversity. We saw this one already. So now I'm going to talk about this MIMO channel. So MIMO channel here, let's say 2 transmit and 2 receive antenna. So this channel coefficient we normally write H11, and this coefficient we write H22. There's a channel coefficient here, we write H21. Here we write H12. Okay, so let's say you transmit X1 here and you transmit X2 here, and your receive signal here, Y1, is x1 into h11, so h11 into x1, and then x2 into this channel, h1 to x2, and some noise w1. Okay, so and y2, the received signal at this point, the antenna came from the first transmit antenna and the second transmit antenna. So h21 into x1 and h22, this channel into x2 and w2. So now you put this received signal y1 and y2 as a vector here, and you will get h11, h12, h21, h22, x1, x2 plus w1 and w2. Okay, so the vector receive signal can be written as the matrix channel into transmit signal plus noise. So this is the MIMO receive signal model. Okay, so that's the equation written here. Y is the vector. Is normally, if you have a, let's say if you have a people say NT transmit antenna, and let's say people normally denote NR receive antenna, your receive signal Y, which is NR into one vector, into H, which is NR into NT matrix, X, this is vector again, this dimension is NT into 1 and plus noise. Okay, so this is the general equation. Okay, if you have a NT transmit antenna, NR receive antenna, the receive vector NR into 1 vector is written as matrix NR into NT matrix, and X transmit signal vector NT into 1 vector, and W is NR into 1. So this is the general receive signal for NR NT transmit antenna and NR receive antenna. Anyway, so this one is for the 2 transmit antenna, 2 receive antenna. This is the way you write receive signal. So here H is the NR by NT fixed channel matrix. Okay, H is the NR, number of receive antenna into number of transmit antenna. So now, once you put all these things in a matrix form, we have a beautiful linear algebra theory can be used to derive many results. Okay, so we will see some of them maybe today. So once we have a matrix channel, we can do a lot of linear algebra techniques. Okay, so one of them is called singular value decomposition. So we can do a singular value decomposition of the channel matrix, like a U lambda into V complex conjugate Hermitian. Okay, so U and V are complex orthonormal matrix, and lambda is a real diagonal matrix contain singular values. I hope you know singular value decomposition. In MATLAB, you can write SVD into H. It will give you a singular value decomposition. You can put U, V, lambda. In MATLAB, if you do, you will get singular value decomposition. How do we get eigenvalue decomposition in MATLAB? You do EIG, H, and you will get eigenvalue decomposition. Okay, E and the lambda, eigenvectors and eigenvalues, etc. Anyway, so if you do a singular value decomposition like this, so your receive signal, let's say this is the equation 1. Okay, I'm multiplying this equation 1 into U Hermitian. What I'm going to get is, okay, U Hermitian into Y and U Hermitian into H. H is that singular value decomposition. U lambda V Hermitian into X. Okay, so here in the The book we wrote like a star. It's not a complex conjugate. It's a Hermitian transpose. Okay, so I'm writing Hermitian transpose like a H here. Okay, and then okay, so you will get this equation. So what I did is I multiply this equation by U Hermitian, and U Hermitian into Y, U Hermitian. H is your SVD. This is the HVD, singular value decomposition. I get this. Okay. Now I denote this guy as a tilde. Okay, Y tilde. And U Hermitian into U, they are orthonormal matrix. This become identity. These guys are identity. Okay, so now I get lambda, and this guy, I denote X tilde, then I get X tilde, and I'm denoting this guy as a W tilde, so this becomes W tilde. So now what happened is, this matrix channel have a, full matrix. It's now turned out to be parallel channel. Did you get what I'm saying is, so you have Y1 tilde, Y2 tilde, etc. Okay, is equal to lambda 1, lambda 2, these are singular value, up to lambda, let's say, n min 0, 0, and you have a x1 tilde and x, tilde and some noise. Okay, so what I did is by doing this SVD decomposition, etc., I changed the matrix channel as a, this is kind of a scalar channel. You can see the yi tilde is lambda I xi tilde and some noise. Okay, so this is like a scalar channel now, scalar parallel channel. This is a scalar parallel channel. Now we can write the capacity and everything easily. So by doing, so that's why the matrix, once you put a matrix channel receive signal, then the beautiful linear algebra theory can be applied, and you can get a lot of insight about the capacity, diversity, degree of freedom gain, etc. Okay, so that's what is shown here. So this one is showing between x tilde and y tilde, there is a parallel channel. Okay, if you see y tilde is here, this is the y tilde, and this is the x tilde. You do all these U Hermitian, etc., etc. You can see this is considered as a spatial parallel channel. Okay, spatial parallel channel, because the off diagonal terms are now 0. Okay, off diagonal terms are 0. So capacity is achieved by water filling over eigenmode of H. Okay. Anybody heard about water filling before? Yeah, water filling. Okay. Okay, so water filling is not coming here, but I'll tell you later on. So, so this all these things are shown in this diagram. So look at the y tilde, this guy, and the input is x tilde, and you can see these are now changed to spatial parallel channel. Okay, so this there's a n min term here. What is this n min term is? N min is minimum of nt comma nr. Okay, so this is called n min. Okay, minimum of nt comma nr. In this case is 2, because true transmit and true receiver, so n min is 2. But you can have 4 receive antenna, 2 transmit antenna. In this case, n min is 2. You can get different values here. So this guy, I'll tell you later on, this guy is called degree of freedom gain, or also called multiplexing gain, this n min. Okay, so your capacity is linearly increased with n min. So if you have a more antennas at the transmitter and receiver, the N-min is the one will give you a capacity boost, okay? So this is called degree of freedom gain. So this one is not exist in the CMO channel or MISO channel because it's always 1, okay? In the CMO channel or MISO channel, or the transmitter antenna 1 or receiver antenna 1, so N-min is 1. But the MIMO case, this N-min is more than 1, it will give you a degree of freedom gain or multiplexing gain. So that's the one I mentioned before. The MIMO will give you a degree of freedom gain, okay? That's one thing here is saying capacity is achieved by water filling over the eigenmodes of H. Maybe we will do a question how to do water filling later on, but for the time being, leave it, okay? Maybe I can explain as well. So what is this water filling is saying is the capacity now is we'll come back to that. So as I said, you know, the linear algebra theory now play a big insight of our MIMO channel. So the rank and the condition number, you may heard about these things. These are linear algebra terms, rank of the matrix, the condition number of the matrix. These all are linear algebra stuff. It is coming here to show, you know, if you have a full rank matrix, what is the, you know, benefit if it is the condition number is if you have a well-conditioned channel matrix, you get more capacity. If you get an ill-conditioned matrix, you won't get the capacity much, etc. Okay, so high SNR. So okay, so there's one thing I'll tell you later on about the water filling. Okay, water filling mean you have a power here, transmit power. You allocate that power according to the channel, the eigenmode. Eigenmode are the lambdas. Eigenmode are the lambdas. You allocate the power according to this eigenmode. But if you have a larger number of high power, you don't, it's called high power mean high SNR. You don't do power allocation. You do equal power allocation. So that's what it says here. High SNR, equal power allocation is optimum. Equal power allocation mean you have a P power, let's say total power is P. You divided, there are NT transmitter antenna, so you spend power here P over NT, okay? You divided by equally to each of these antenna, so that's called equal power allocation. Okay, so that's what it's saying. Equal power allocation is optimum in high SNR. The capacity can be written as this form. So how do we get that capacity? Capacity is 1 plus SNR, okay? So SNR is, this guy is SNR, okay? So 1 plus SNR, there are K N-min channels are there actually, okay? There are N-min channel, is over there, I say K here, so there are N-min channel. So the capacity is a summation of these parallel channel. So that's why there is a summation coming here. So, okay, so this is the capacity, okay? So this can be written as at high SNR, as I said, wireless communication, we talk about high SNR, low SNR very often. High SNR, what you do is we can, this guy is very big. This guy is very big. This is SNR, it's big. Compared to 1, you ignore this guy, okay? So if you ignore this guy, you can write like this, okay? So your capacity formula is going to be summation of I is equal to 1 to, let's say, N-min, okay, log 1 plus P over, I'll keep a K here, P over K, the power allocation, and lambda I squared is the gain of this channel, and divide by n naught. Okay? So high SNR is approximation. High SNR approximation means you ignore this 1. So what you do is equation is going to come like 1 over k log p over k lambda I squared over n naught. This is the approximation. You know high SNR. This guy is very big compared to 1, so you can ignore the 1. You can write like this. Now the log 2 term are there, so you can write this as a, you can write like p over n naught as a SNR. So you can write, you know, k into log SNR. So what I did is p over n naught as a SNR. There are summation 1 to k, so k into SNR, and you can write a remaining term as a summation log lambda I squared over k. So you can write like this. So that's what is written here. Okay, so as soon as you ignore this 1, you have a 2 term. So log product can be written as a summation, and you can write like this. So that's what is written there. K is the number of non-zero singular values. Okay, so what is the, you know, here lambda I is a singular value of H matrix. Okay, what is lambda I squared? Lambda I squared is a eigenvalue of this guy. Okay, so I hope you get this one. Lambda I is the singular value of H matrix, but lambda I squared is an eigenvalue of this matrix. Okay, anyway, so the next thing is called condition number. The condition number of the matrix is defined by maximum lambda I over minimum lambda I. If this guy, condition number, is very close to 1, then your matrix is very, you know, good condition, okay? And then, in other words, the maximum lambda I over minimum lambda I is 1 mean your maximum singular value and minimum singular value of the matrix is almost same. That's why it's become 1. Then you will get a high capacity. So you have all the eigenmodes or the lambda is a good equal value. You get lot of high capacity of the channel. Okay, but if you have a channel matrix have a ill condition, in that case your minimum eigenvalues are very, very small compared to maximum eigenvalues. Okay, so you put maximum, or these guys are very small. If the matrix is ill condition, then this condition number become very large, and that case you won't get capacity. Okay, so in order to get high capacity, your channel here had to have a rich scattering. Okay, between transmitter and receiver, your channel had to be a rich scattering. If you have a rich scattering in between transmitter and receiver, your H matrix going to have a good condition number. Good condition number, you will get capacity. If it is a don't have a rich scattering, this guy is going to get a, you know, ill condition matrix, and you won't get that much capacity. So rich scattering means a lot of scattering had to happen transmitter receiver. If the transmitter receiver is very close together, you have a line of sight environment. So then this guy is not going to be full rank, and it's also going to have a ill condition, and you won't get high capacity. So this is the beauty of linear algebra theory application to channel capacity formulas. Okay. Any question? Okay, so transmitter receiver CSI. CSI mean channel state information. CSI mean channel state information. Okay, so this slide is saying transmitter and receiver CSI. So transmitter also know the channel. Okay, transmitter receiver CSI mean this channel is known at the transmitter and the receiver as well. Then only you can do this kind of you can multiply the transmit signal by V Hermitian and etc. Okay, so That's what this slide is saying about. If the transmitter and receiver know the channel state information, CSI, we can decompose the MIMO channel into bunch of orthogonal subchannels. That's what we did, and then each of these subchannel we can send independently coded signal. We can do any AWGN code. We can do a turbo code here and send through one of the eigenmode. You can do another stream, another turbo code, and send through the another eigenmode, etc. And it is going to be min of nt comma nr. So if you have a lot of transmitter antenna compared to receiver antenna, some of the transmitter antenna you won't be able to send information. Okay, so that's what this slide is talking about. So you can send each of these eigenmode independently coded stream. Okay. In order to do that, you need to know the transmitter, know the channel. Then only you can multiply by V Hermitian here. You do a pre-processing here. We multiply by channel information. Okay, as one of the SVD matrix here. So in order to do that, you need to know the channel at the transmitter, and the receiver you multiply by U Hermitian here. Okay, so the next slide is showing this is very similar to OFDM. Okay, I hope you know what is OFDM is. In OFDM also, this is an analogy with OFDM. OFDM also, we do a inverse Fourier transform at the transmitter and discrete Fourier transform at the receiver. Okay, so here also you are multiplying by V at the transmitter, you are multiplying by U at the receiver. So these are very similar, the MIMO case and the OFDM. OFDM, this is application to a single input, single output system, but you do inverse discrete Fourier transform at the transmitter and discrete Fourier transform at the receiver. So this slide is saying there is an analogy between OFDM and the MIMO channel. Okay, so but there is a major difference. In MIMO, we multiply U and V matrices. That depends on the channel. But in OFDM, you multiply by the inverse discrete Fourier transform and discrete Fourier transform. They are not depends on the channel. Okay, in OFDM, the inverse Fourier transform and the discrete Fourier transform matrices do not depend on the channel. So that's one message in this slide. Any question? Okay. So let me continue. The channel receiver CSI only. Okay. As I said, receiver know the channel is the good assumption. Okay. Receiver know the channel all the time. Your 3G, 4G, 5G phone always estimate, receiver always estimate the channel. Okay. Base station estimate the channel for each of the coherent time. Your mobile phone estimate the channel each of the coherent time as well. So this is the kind of a reasonable assumption, but transmitter know the channel is a little bit more, okay? But 4G base station assume transmitter know the channel in order to do precoding, which I will talk tomorrow in the FDD mode. Okay, channel matrix H and its singular value lambda i's are random and unknown to the transmitter. So okay, yes, now the transmitter does not know the channel, so they cannot do multiply the transmitted signal by the one of the SVD matrix V. So they cannot do that because transmitter does not know the channel. So in that case, this matrix is going to be just an identity matrix. So it's like a Q become identity matrix because transmitter does not know the channel. So if the transmitter does not know the channel, it cannot do a power allocation, like a water-filling power allocation, etc. Then in that case, it do equal power allocation like this. Okay. Okay. So what it's saying is channel matrix H and the singular value lambda I squared are random and unknown to the transmitter. has to fix Q and power allocation independent of H, and it's normally do a uniform power allocation is optimum in many cases. So in this case, it cannot do any precoding or anything, so just do identity matrix here. So it turned out to be uniform power allocation is optimum if the receiver transmitter does not know the channel. It is not trivial to come up with the capacity achieving architecture if we don't know the channel at the transmitter. So, so now we talk about capacity. So we have already wrote the capacity formula here for the MIMO system. The MIMO system capacity can be written as this formula because there are n parallel channel. N mean parallel channel, so there is a capacity formula, this one. Each of these capacity of the parallel channel are add together, okay? This can be written as log determinant formula, okay? So now you see a lot of linear algebra is coming here. So you know, what is the eigenvalue of this guy? So eigenvalue of this matrix. So eigenvalue of this matrix is actually 1 plus, you know, this SNR over NT into lambda I squared. So this is the eigenvalue of this matrix, okay? So determinant of this matrix, let's say this is alpha. So determinant of this matrix, det of that matrix, is going to be product of eigenvalues lambda I, okay? So log product is become summation, okay? So this is the, I hope you understand this. So eigenvalue of this matrix, identity matrix plus SNRNT over H into H Hermitian. I told you this lambda, we start with this lambda as a SVD, singular value of H matrix. But lambda I squared is the eigenvalue of H into H Hermitian matrix, okay? So this lambda squared now, which is the eigenvalue of this matrix, H into H Hermitian matrix, H into H Hermitian matrix. So this is the eigenvalues, okay? Anyway, so the eigenvalue of all these matrix are 1 plus P over NT lambda I squared over N naught. So determinant of matrix is a product of eigenvalue. And product of eigenvalue, in front of that you have log, so it's log product is written as summation. So that's the formula for the first equation. I hope you got it, okay? So I'll repeat again. H have a singular value lambda, but lambda squared is the eigenvalue of H into H Hermitian, okay? And this matrix have an eigenvalue, these guys are eigenvalues. And determinant of this matrix is product of eigenvalues. So this is, you can write as a product of eigenvalue, let's say lambda alpha. So product of, then you take a log in product, and it can be written as a sum, okay? So this is, I hope that you understand. So MIMO capacity is log determinant I plus SNR over NT H into H Hermitian. So this is the channel capacity formula for MIMO case. So anyway, in this case, okay, so there are two capacity we normally define. H is a channel between transmitter and receiver. This H is the channel is a random variable, okay? Channel is a random variable. I told you channel will take a random realization and stay constant for particular time and take another random realization, stay constant for particular coherent time and take another random realization, etc., etc. So this guy is random, this guy is random. So all these capacities are random, all these capacities are random. So random variable, if you take a mean of that random variable, if we take a mean of this guy, this is random. The H is random, so determinant is random. In front of log is also random. So all these things are random variable. If we take a mean of that guy, this guy, this is called ergodic capacity or mean capacity. So you take a mean expectation of the same thing. So this is called, so we talk about two fading, fast fading and slow fading. In the fast fading case, the information theoretic measure is called ergodic capacity or mean capacity. So that what is mean capacity or ergodic capacity? It's the expectation of this random variable. That is the mean. So that's what fast fading is here, okay? So it's the expectation of this random variable. This is a single, this is, even though this guy is matrix, is when you take determinant, this becomes scalar. It's a scalar random variable, okay? This is the mean capacity. It's a mean of this random variable is this. So this is, if you are in the talking about writing papers with the fast fading channel, your information theoretic measure is the mean capacity or ergodic capacity. But if you are talking about your channel as a slow fading channel, your information theoretic measure is outage probability and outage capacity. So what is outage capacity and outage probability mean? So you are given a slow fading channel, you assume that this channel can support rate R. You assume it's a slow fading channel, your coherent time is very large. You assume this channel can support R bits per second per hertz, something like that. And then you, according to that R rate, you do coding and everything, transmitter, receiver design, you transmit, okay? Whenever that channel become very bad or in the deep fade, it won't support that your rate R. In that case, you are in outage. So what is the probability you are in outage is called outage probability, okay? So if somebody gave you outage probability, so let's say you are working in Qualcomm or somewhere, so you are asked to design a communication system, and your manager saying, I will be happy my outage probability epsilon is 0.01. So what does that mean? You take 100 realization of the channel, one of the channel is outage, so outage probability is 0.01. If what is epsilon is 0.1 mean, outage probability is 0.1 mean, you take 10 realization of the channel, only one of the channel will be outage. So you are given an outage probability, this guy, you go and find this R according to this formula, that R is the outage capacity, okay? So the information theoretic measure in the slow fading channel is outage probability and outage capacity. Information theoretic measure for the fast fading channel is the ergodic capacity or mean capacity. Okay, so this is very important slide. Any question on that? Okay, so because of this log determinant formula, you will get huge capacity. I'll show you in a minute. Okay, so this is the you talk about MIMO all the time. You heard about MIMO. The benefit of MIMO is shown in this slide. Okay, so you see here we are talking about fast fading channel, IID relay fading. IID relay fading means all these channel coefficients are independently distributed. IID. So IID, all of them are independently. Okay, your channel H. Channel H is a made element Hij. Okay, this is what is the dimension? This dimension is NR into NT. NR receiver antenna, NT transmitter antenna. Your Hij are complex normal, zero mean, variant 1. Okay, and they are independent. Each of these guys are independent, so we call IID relay fading channel. So that's the meaning. Okay, you have a channel. All of these elements are complex normal, zero mean 1, and they are all independent. Then this channel is called IID relay fading channel. Okay, so let's look at the capacity, bits per second per hertz. So what is the maximum rate you can transmit? Reliably, it's the capacity, bits per second per hertz. This is SNR, okay? This is SNR. There are three curves are here. Let's look at this one, this guy, the red dot curve. Oh, that curve is for one transmit antenna and one receive antenna. NT is equal to 1, NR is equal to 1, okay? Your capacity. Let's look at SNR is equal to 2 dB, so 20 dB. SNR is equal to 20 dB. What is the capacity you are getting? You go here, you are getting 5 bits per second per hertz, okay? 20 dB, you go here, and you go here, you are getting 5 bits per second, okay? This is a CISO case, single input, single output case. Same here, this one is for MIMO case, 4 transmit NNR and 4 receive NNR. So your power is same, 20 dB. You go here and you get 20 bits per second per hertz. So your capacity increased by 4 times, okay? CISO case, single input, single output case, your capacity is 5 bits per second per hertz. For the MIMO case, same 20 dB, you didn't increase the power. Even though you are putting more transmit NNR, but your transmit power is same for single NNR case, and some transmit power is same for the MIMO case as well. You are getting 20 bits per second. That's the beauty of MIMO. So you never increase, you put more antenna, but you never increase the power. Capacity increase 4 times. What is that 4 come from? That 4 is actually min of 4 transmit NT comma NR. So this is the multiplexing gain. In this case, transmit NNR is 4, receive NNR is 4, so the min, this is 4 times. So that's why 4 into 5 is 20, okay? You get, so you see that the beauty of MIMO is giving a 4-time improvement, even though you are talking SNR is the same SNR for CISO case, MISO case. And there's another plot here, the blue one. This is a CMO channel, single input, multiple output channel, CMO channel. You will get some gain here compared to CISO gain. That gain is not spatial multiplexing gain. This gain is because you will get a little bit more capacity. This is not due to spatial multiplexing gain or degree of freedom gain. This is due to the receiver beamforming, the power gain that you are getting here. That's why you are getting a little bit more, okay? So yeah, this is the beauty of MIMO, will give you more capacity. If you put more antennas, you will get more capacity. But when you put more antenna at the transmitter and receiver, you are not increasing the power. Power is same, but capacity is increasing. So here is again, the degree of freedom gain is min NT comma NR. So this is the degree of freedom gain, min NT comma NR, determine the highest NR slope. I will tell you in a minute. So this is the plot same as the previous slide. This is the previous slide, 4 and transmit NR, 4 receive NR. I told you, you are getting a 20 bits per second, which is a 4 times compared to the CISO case. Now look at here, this is 8 transmit NR, 8 receive NR. Same 20 dB, you go here, you get 40. So 8 times 5, 8 into 5 is 40. So you get 8 multiplexing gain or degree of freedom gain. Now the min NT comma NR, which is 8, and you are getting capacity improvement 8 times more. 5 into 8 is 40 bits per second per hertz. Okay, so this is the, this MIMO theory is the one that now you are enjoying, a larger capacity in your 4G and 5G phones because of this, okay? And 5G phones, we are talking about massive MIMO, so we don't talk about 8 antenna, 4 antenna, we talk about, 64 antenna, 128 antenna, even millimeter wave, you talk about 512 antennas, etc. So a lot of antennas will give you a lot of array gain, etc. So you don't, if you put more antennas, you are not putting more power in the transmitter, same power, but it will give you capacity improvement. Any question? Yeah.
Same multiplexing gain, you will get in both the cases of slow fading and fast fading?
Yes. Yeah. You need to do, to get that, you need to do different transmission techniques. That's called B blast and D blast. Yes, I'll tell you in a minute, later on. Yes.
Basically, in any given system, is both the slow fading and fast fading scenarios exist in the same system?
Yeah, it depends, of course, yes. It depends on the scenario. So if you are, walking with the phone is a slow fading. If you are in the high-speed train, it's a fast fading channel. Yeah.
So in the same system, you take this both slow fading scenario or the fast fading?
It's, okay. It depends on the environment.
Automatically it will adjust.
Yeah. So if it is a high-speed train, you are experiencing the fast fading channel. If you are walking, through and using the phone, your channel is slow fading channel. And slow fading and fast fading channels will have a different transmission techniques and all these things. Yeah. Okay, so that's one more thing. Saying high SNR slope. Okay, so this is the high SNR regime. Okay, this slope is give you a degree of freedom gain. Okay, so from this plot you will see this slope is kind of a 8 and this slope is 4. So that's what it's saying. The degree of freedom gain determine the high SNR slope. Similarly, if you have a bitter rate curve, if you have a bitter rate curve here, okay, it's like this, probability of error. The high SNR slope, this slope will give you the diversity order. Okay, the high SNR slope will give you the diversity order. In the capacity plot, the high SNR slope will give you a degree of freedom gain. Okay, so there are many insight you will see from the probability error curve and the capacity curve, etc. So there are many things are happening here. High SNR slope in the probability of error curve is giving you degree of freedom, diversity order. This is diversity order. Here it will give you a degree of freedom gain or spatial multiplexing gain. Any other question? Okay, so any other question? Well, I hope you are following with me. So now this is all high SNR. So let's talk about the low SNR case. Okay, so no, next one. Okay, this is a low SNR regime. So we talk about low SNR regime. Okay, so in CDMA. System operate at low SNR regime. Okay, anyway, we'll come in a minute. So this is a low SNR regime. This plot is showing MIMO and CMO case results. Okay, so you see here this. I hope you see this. The y-axis is capacity, normalized capacity divided by CISO capacity. Okay. So this one is for the blue curve is for the MIMO case, and this red curve is for the CMO case, single input, multiple output case, okay, CMO case. You can see at the low SNR regime, this is the low SNR regime. Why won't we are interested in low SNR regime? As I said, CDMA normally operate in the low SNR regime. In that case, MIMO and CMO are giving same performance. So, then you ask the question, if I am using CDMA system, do I really want a MIMO system? The answer is mainly no. You don't need a MIMO system if you are operating at the low SNR regime. Even though in the point of view of capacity, you don't need a MIMO system if you are operating at the low SNR regime. Okay, but there are still MIMO will give you some another benefit of interference cancellation, etc. But capacity point of view, you are in the low SNR regime. You don't need a MIMO. So that's the message of this slide. So so nature of the performance gain, high SNR, degree of freedom gain, which is a min NT, NR for the degree of freedom gain. MIMO is crucial. Okay, this gain is called degree of freedom gain or spatial multiplexing gain. At low SNR, NR-fold power gain, only need a multiple receive NR. CMO channel is good enough. Okay, you don't need a MIMO channel. At all SNR, this degree of freedom gain due to combination of both effect. Okay. So some questions are here. Should one blindly overlay MIMO technology on the CDMA universal reuse system? Because this CDMA system operate at low SNR regime, MIMO gain is mainly receive NR power gain. So that's what I said. You know, if you are operating at low SNR regime, you don't need a MIMO system. But having MIMO system, you know, you can get some other benefit of canceling interference, etc. So which SNR that you are operating also very important thing to when you are designing a wireless communication system. So now we can talk about transceiver architecture. So this is called VBLAST, okay, vertical Bell Laboratory layer space architecture. This is, you know, this architecture is proposed in Bell Lab in New Jersey, early in 1990s to 2000 time. So this is called VBLAST architecture. This is for fast fading channel, okay? So can get a performance gain by sending independent. So this is kind of a surprising result. So okay, you send an independently coded stream through the MIMO channel. All these stream will interfere at the receiver, and you had to you know, extract each of these stream at the receiver. Okay, so you need to do a clever signal processing at the receiver. Okay, so that's what it's saying. Can get a performance gain by sending independent coded stream on each of these transmit antenna, and you need to do a joint decoding here, because each of the antenna is sending a independently coded stream, okay, independently coded stream. So at the receiver, all the stream will be interfere each other, and you need a clever signal processing technique to extract each of the transmit stream. Okay, so it's called. This is surprising. Even though this independently stream interfere at the receiver, we can still decode all these independent stream and get the degree of freedom gain. How to get the degree of freedom even when the streams are interfere with each other. Okay, so these Bell Lab people come up with a blast architecture that can decode, okay, decode this stream independently and decode this stream in the independent coded stream and get the capacity. So you need a receiver here, which is the one I'm going to talk later on. So the receiver here, you are sending an independent stream. Okay, you have a MIMO system here. Okay, you have a MIMO system here. NT transmit antenna. You have a receive antenna, NR receive antenna. Each of these guys are sending independent stream. Okay, okay. So you have a big video that you wanted to send, let's say, big video that you need to send, okay, or image you need to send. You divide that stream like this, and this stream 1 will go through antenna 1, stream 2 go through antenna 2, etc., etc. All this stream will be coded independently through this antenna, this antenna, this antenna. Then at the receiver, let's say you have a risk scattering here, and you receive this each of these stream together, and you need to decode each of these stream back and put it back this way to get your video back. Okay, so you need a very high signal processing techniques here. So you can of course use some ML decoding, maximum likelihood decoder here, but that is very complex. So we need to come up with some receiver design here. So the story is that I'm going to tell you, the easy receiver is a zero forcing receiver, and it won't achieve the full capacity. Then I will talk about MMSC receiver. That is also not going to achieve the capacity. And then I'll talk about MMSC with SIC, successive interference cancellation techniques. This is a nonlinear receiver. These are linear receivers. The ML receiver that we can use here achieve capacity, but that is a nonlinear receiver. It is also very complex to implement. Nobody implement maximum likelihood decoder receiver. So we had to go zero forcing or MMSC receiver. These are linear receivers that won't give you maximum capacity. So the channel capacity, log determinant formula, give you the maximum rate that you can transmit, but it won't tell you, Channon won't tell us how to realize that capacity. Channon didn't say that. Channon said, this is the maximum capacity you can achieve, and he didn't say to us how to realize that. So similarly here, these receivers not going to achieve a channel capacity. But this guy, MMSC with SIG, will achieve the capacity, and that is the one we will be studying. All these things we will be studying in the rest of the lectures. Any question? I think maybe we can continue this one next time. Yeah, we can discuss now. So we will be studying this receiver here, zero forcing receiver, and MMSC receiver, and zero forcing receiver. Did you heard about the word zero forcing receiver? This is called, there are many names for this one as well. Interference nulling, decorrelator, zero forcing receiver. There are 3 names here. And MMSC is a minimum mean square error receiver, and this one is minimum mean square error successive interference cancellation. That is the one achieve the capacity that we saw the log determinant formula. Anyway, any question?
Yeah, please ask questions. We should be able to understand, right, whether you are understanding or not.
Yeah.
Huh? These understandable, huh? If you're having any doubts or if you don't understand anything, please ask questions.
Okay, here I have a question. Okay.
So diversity affects capacity also. Diversity.
Diversity is going to affect the bit error performance. Yes.
So indirectly it is also impacting on the channel.
Capacity also. Yes. Yeah.
MIMO is providing higher gain when compared to sigma MISO and
Oh, yes.
the two other.
Yeah.
So whether which like antenna diversity or receiver diversity gives more.
Okay. In MIMO, we have both transmit diversity, receiver diversity all together. Okay, we have both. Antenna diversity have 2 things. One is transmit diversity and receiver diversity.
Both will be playing major role in enhancing capacity.
In the MIMO system, yes. Sorry, anything? Yeah. Yeah. CISO capacity, you know that, okay? You are asking the CISO capacity. That's just log 1 plus SNR. So this is the CISO capacity. So this is a log 1 plus SNR. In the MIMO case, you will get a determinant and summation will come here. So that's why you are getting a MIMO larger capacity. So did I answer your question? So CISO capacity is just log 1 plus SNR. Yeah? That's what your question? Yeah. If you have interference also in the environment, then your capacity formula, you had to use log 2 1 plus signaling interference plus noise ratio. Okay, if there's interference. SNR is signal power divided by the noise power. But if you have interference also, then you talk about SANR, signal to interference plus noise ratio, signal power divided by the noise power and plus the interference power. Yeah. CSI means channel state information. Okay, so CSI mean channel state information. Let's say CSI mean channel state information, and then another CSI mean channel state information. CSIR mean channel state information at the receiver. So the receiver know the full channel. Receiver know the full channel for particular coherent time. Receiver know the full channel H matrix. Then only it can do zero forcing, MMSC, etc. Because it need a channel knowledge. And CSI, CSIT mean channel state information at the transmitter. Transmitter also somehow know the channel, okay? Or the partial channel knowledge is known. Some part of the knowledge is known at the transmitter,
So it is giving information about the nature and behavior of the channel.
The full channel is known.
Yeah, the nature, how the channel behaves and everything is given by the CSI.
Yeah, CSI, yes. Yeah.
And most of the times we hear the word imperfect CSI.
Yeah. Imperfect mean you need to, okay, so how do we estimate the channel? Okay, when you, how do we estimate the channel is the transmitter will send you some pilot sequence. Okay, pilot sequence mean in the standard, 3GPP standard, there are pilot sequence available. So transmitter will send that pilot signal, and the receiver knows what is transmitted. Receiver knows what is transmitted because of the pilot. Then based on that, receiver estimate the channel, okay? So during the training, receive signal, let's say this is NR into how many pilot, a long pilot you are sending, let's say T, and this is H into X, X is NT into that T pilot duration, so plus noise, and the receiver, of course, know the receive signal, and also know the transmitted pilot signal, and that it will estimate this one using least square techniques, okay, or zero forcing technique. It will estimate the channel estimation. So the channel estimation is the channel is actually estimated. So it's estimated channel. The estimated channel is actually a true channel plus some delta estimation error. So in reality, channels are estimated. It's not a true channel. So there is uncertainty as well, which is called channel uncertainty delta. So your phone and all these things are based on estimated channel. Is still working fine, but it's not a perfect channel. It's estimated channel. So always there is uncertainty, channel estimation uncertainty. It depends on the SNR and all this. If you are very close to the base station and your SNR is good, you will estimate the channel accurately. If you are in the cell edge, your channel is, SNR is low, your estimation will be uncertainty involved. That's why you are getting a bad quality estimation and drop codes and all these things. Yeah. So if you are doing performance analysis, you start with the perfect channel and then you introduce channel uncertainties, and there will be some degradation in the performance due to channel estimation error.
And if you elaborate on water filling, you told at the end of this.
Yeah. Water filling, okay. So So what water filling mean? So MIMO case, you plot versus y-axis n node. This is lambda. Lambdas are your singular value decomposition values. Okay. Then 1 over you plot 1 over lambda I. So it is going like this. Okay, it's going to be like this. I'm just drawing randomly. You know, it's going like this, let's say. So your first lambda I, a node over lambda I is this one, and the second eigenmode is second eigen singular value mode is, let's say, this one, third, fourth, fifth, sixth, etc. So you plot it like this, and then you consider your power as a water. Okay, your power as a water, you put your water inside. Okay, so once you put the water inside, it is going to be, depends on how much water you have or how much power you have. It is, let's say it's going like this. Okay, it's going like that. And then you allocate power for that eigenmode. This is the power allocation that you are going to allocate. Okay, so if you have a good eigenmode, this is very good value. 1 over this value will be smaller. Okay, so here, if you have a very good eigenmode, so this guy is very large, so 1 over is very small. So in that case, you allocate more power. Okay, the water filling power allocation is you send the more power to good channel and less power to bad channel. Okay, so then only you will get capacity. Okay, so in this case, lambda is very good. In this case, 1 over lambda is very small. You allocate more power. Okay, so the power allocation P star I is defined as power allocation P star I is defined as, this one is, let's say, mu. This mu is depends on how much power you have or how much water you have. If you have more power, this mu level is going up and down. So mu minus this one, n node over lambda I, this is the power allocation. Okay, this is the power allocation. So this is the power allocation. This is the power allocation. How do we get that the equation? Mu minus this guy. This guy is n node over lambda I, and there is a plus sign here. Okay, if it is positive, you allocate power. In this case, it's going to be negative. It's a bad channel. Don't put power. Okay, the information theory is saying if you have a bad channel, don't communicate. Okay, so in this case, your power allocation is 0. Okay, and this case also your bad mode and you don't allocate power. So information theory is saying if you have a bad channel, don't communicate. But if you have a good channel, try to put more power and communicate. That's what information theory is saying. But in reality, fairness and all these things are there. You know, so if you have a bad channel, if somebody is in the cell H, he is having a bad channel. So information theory is saying don't transmit to him. Okay, but for the fairness, we transmit as well. Okay, but you know, information theory point of view, you know, sending to bad channel person is a wastage of resources. Okay, so but when you consider fairness, we need to serve that person as well. So that is kind of a not information theoretically optimum, but we still send some power to that guy to serve as well. So the power allocation is saying if you have a good channel, you put more power. If you have a bad channel, don't transmit. And according to, yeah, this is called water filling power allocation. Okay, you plot n node over lambda I, and your power as a water, you put this water into this vessel, and this is the power allocation. So this plus sign mean, this plus sign mean min x comma 0. Yeah, so if it is negative, you put 0. If it is plus, you will put that value. That's this. Yeah, so this, yeah, the information theory is there saying if it is good channel, you transmit more power, but if it is a bad channel, don't transmit. But fairness issue, when you consider even if the bad channel, we will send some power. But that is actually not optimum. Yeah. CSI? C. Channel quality indicator is also telling about the channel between transmitter, the quality of the channel, okay? CSI mean is the full channel information. The CQI is another indicator, but it's not the exact channel is given. Okay, is it's going to be a, if you have a good SNR, your CQI is a large value as well. Yes, it's a proportional mapping. The water film power allocation, here for the MIMO case, I explained, you can do OFDMs also, different in that case, X-axis is going to be the subcarrier, and yeah, subcarriers. So whichever subcarrier have a good channel, we put more power. Whichever some subcarrier is bad channel, we put less power, etc. There are some questions. Yeah, we will do some question in that later on. Any other question?
Can you tell me in which conditions we can use transmit diversity and in which conditions we can use the receive diversity?
So you know, transmit diversity, if you do need to do transmit diversity, you should have a more transmit antenna, and you should also have a channel knowledge at the transmitter. Then only you can do transmit beamforming and get the transmit diversity. Yeah, receiver diversity, if you have a multiple receiver antenna, you will get receiver diversity automatically.
Doubt is in application scenario. Is there any specific application scenario?
So, okay, so one of the application I explained to you in the 3G scenarios, our base station normally have 2 antennas, and when you transmit to downlink user, it will do a transmit beamforming, and when user send information uplink, we use a receiver beamforming, also receiver diversity, okay? So we cannot get both because one of them have one antenna. Okay, in 4G also similar, but now we have massive MIMO, and it's have a little bit different effect, array gain. 5G phones are, you know, still you are using one antenna at the receiver, but because of the large number of antenna at the transmitter, we are getting the array gain, or you are getting a pencil beam to you, and that you know lead to bigger array gain, less interference as well. Okay, less interference. So your signal to interference plus noise ratio is very good. So because of that, yes. But in the millimeter wave frequency, your phone have more antenna, 4 or 8 antenna possible, 5G phones. Any other question? Okay, we can take a break then, yeah?